All right, so what we're going to talk about now are sequences. Sequences are going to be a set of numbers related somehow. And what we will have here is that a sequence will converge if the set of numbers tend towards something. So if it goes to a horizontal asymptote, they can also alternate as it goes towards that horizontal asymptote, but as long as it's converging to a finite value, then it's said to converge. It diverges if the set of numbers is going off to positive infinity or negative infinity, or if the set of numbers alternates but don't tend towards a horizontal asymptote. Sometimes when we want to talk about the limits of something converging, we look at individual terms because they're a little bit harder for us to see these now. The limits are definitely harder. So looking at this first one, the curly braces help us know that it is a sequence. We usually start at 1, but there's no reason we can't start at 0. So if we start at 1, we would get positive 3. If we plug in 2, this will now be squared, so that'll be a positive 4. And you can see that if n is odd, we're going to get 2. If n is even, we're going to get 4. So that limit is not tending towards something, so it does not exist. And therefore, this sequence convergence does not exist. The sequence diverges. And again, we're talking about a sequence. We have this set of numbers, bn, and we can either write out a bunch of the numbers, and you can see that they're getting closer and closer to negative 1/2, or because the degrees are equal, it's the ratio of the leading coefficients, which means the limit is negative 1/2, which means the sequence converges to negative 1/2. 3, same thing, we can write out a couple of the terms and kind of see what's going on here. The next thing we can look at again is the limit. Sometimes in Calc 2, instead of doing L'Hopital's, we just pay attention to the growth rates. So what grows faster? 2 to the n. This exponential is going to grow much faster than this n. So this limit is going to 0. Therefore, the sequence converges to 0 also. Here's our growth rates that we've talked about before. N factorial grows the fastest, then your geometrics, then your polynomials, and remember that natural log grows very, very slow. We have 2 different types of formulas we've talked about over the years. The first one you guys have talked about is explicit formula. This is something like this, where it's very easy to get the next term. If I want to find n equals 1, the first term, I just plug in 1. If I want to find the second term, I just plug n equals 2. If we want the 100th term, we would just plug in n equals 100. So on an explicit formula, this sequence is generated by using the term number. We've seen that before. You've had the arithmetic series before. You've also had geometric series where it looks like a n is equal to a 1 r to the n minus 1. The other type of sequence you guys have talked about briefly in the past is recursive. In recursive, it requires the previous terms in order to generate the next one. It's not easy to find like the 100th term. To find the 100th term, you'd have to find all 99 in front of it. Right, the next one is a Fibonacci. This is an example of the recursive. So to do the Fibonacci, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8. So you can see to generate the next term, we add the 2 previous terms. So you can see right here, I could write that to get the nth term, I would use the n minus 1 and n minus 2 terms. If I want to find the n plus 1 term, we use the 2 previous. Now, if we're trying to find a certain term, we have to use previous terms, and we have to have initial conditions or seeds. We can't say that we're just going to add the 2 previous numbers if we don't tell it to where to start. So here on this recursive, you see I'm using an to get the next term, an plus 1. They tell it starts at 4. So right here is n is equal to 1. Right here, n is equal to 2, which means we're going to take n equals 1 and plug it back in here. And that's how we get the next term. And again, to do the next one, we plug it in again. So you do 2 times 7 minus 1, and that'll give us the next term. And you can see that they get bigger and bigger, so they're said to diverge. Now, in general, we know a sequence converges if its limit is finite and exists. So looking right here, we can see this one's getting bigger and bigger and bigger, so we know that it does diverge. And this right here is arithmetic. You can see it goes up by 4 each time. So what I think of that as is the slope. So it's going up by 4. Now if I want this first one to be when I plug in n equals 1, because that right here is n equals 1, that tells us a1 is equal to 3. So if a1 is equal to 3, when n is equal to 1, that means that we're going to have to put a minus 1 here to make sure that it matches. And then you can see if n is equal to 2, I would in fact get the second term. Now sometimes these are harder to generate than that, but you can kind of look at the patterns. You can just look at the tops here, 3, 4, 5, 6. I'm guessing this would have been 7. It's going up by 1, so that's your slope right here. And again, if I plug in 1, I want to get 3, which means we need that plus 2. The other thing I notice is that the bottom is going up by 3. So again, the bottom piece is arithmetic. It's going up by 3. If I want this first term to be 2, I have to subtract 1. And the last thing I notice about this is that it alternates. So it's going positive, negative, positive, negative. So because it's going positive, negative, positive, negative, we have this alternating piece. The alternating piece is either negative 1 to the n or negative 1 to the n plus 1. Since I want this first term to be n equals 1 and I want it to be positive, I would need this to be even. So I can use n plus 1 or n minus 1. My sequence is going to 1/3, but it's alternating. So it's going positive 1/3, negative 1/3, positive 1/3, negative 1/3. So it diverges. Same thing with the next one. We can see we got some consistencies here. We've all got 1 right here. And then the top is going like 1, 3, 7, 15. The bottom, 2, 4, 8, 16. Looking at the bottom, that's like 2 to the n. And the top is exactly 1 less. And this one would converge, and it would converge to 2. And again, that would be the sequence is converging to 2. So this sequence is converging to 2. The next one is definitely going to diverge. You can see it's getting bigger and bigger and bigger. But if you notice, my first common difference, those are not common. Well, I shouldn't call it a common difference. The differences are not common. But if I do my second differences, they are in fact common. That means that the equation, the formula, had to come from n squared. If your third difference was common, then it came from n cubed. So that gives us a hint that it was n squared. Another thing we can try is write the term numbers up on top. And sometimes we can see some pattern with that. And see 5 squared minus 1, 4 squared minus 1, and that gives us our sequences. And the next ones, again, are converge, diverge, and we're talking about the sequence. So again, write out a couple terms, 0, 2, 0, 2. Limit does not exist, so therefore the sequence diverges. This one right here, the degrees are equal. So this sequence is converging to 3/5. The degree at the top is less than the degree at the bottom, so the limit is 0 and the sequence converges. 12, it is alternating, but you see this is getting bigger and bigger and bigger on the bottom. So the top is going between 0 and 2, 0 and 2, but this bottom's getting infinitely bigger, so the ratio goes down to 0, and therefore the sequence converges. We can factor some factorials, converges, and this was the fancy limit we've talked about before. It's just e, so therefore the sequence converges. All right, so the next thing we're going to talk about is the convergence, divergence of an infinite series. So first, looking at the definition, an infinite series is one that you're going to keep going from 1 to infinity. An is the term number at the nth position. If we're talking about the partial sums, that means if I'm finding S1, that's a sum of the first term. S2 is the sum of the first two terms, and so on and so forth. So in general, the Sn sum is going to be the Sn minus 1 sum plus the new term that was being added. Monotonic means that it either always increases or always decreases. And bounded just means there's some place above or below that the sequence isn't going to get bigger than or smaller than. So the next thing we talked about was just your standard sequences that you've done your whole life, just making sure that we still remember how to do them. Remember, this was sigma. This is where you start. So we're going to start with plugging in n equals 2. If I plug n equals 2 into this formula, we get 7. Then we increase that by 1 until we get to n equals 5, so n is equal to 3. I plug 3 in there to get 9. And increase it by 1, so n is equal to 4. Plug it in. N is equal to 5. That's the last one we're going to do. And then we add them together. And that's the sum. And this one is the same thing. It's just we started at 3 and went to 7, and we were adding the squares. Now, it is said that if every single Sn converges, meaning it's finite, then the sum is also going to converge. If any of the partial sums is infinite, then the full sum will be infinite. So in this first one, we're just finding S1, S2, and S3. So S1 is just the first term, S2 is the first two terms, and S3 is the first three terms. All right, so the next one is just how you would probably see this on the AP test. Right here it says, the infinite series has this partial sum. What is the sum of the sequence? Well, if all of these converge to a number, then the series is going to converge to that number. But looking at this does not exist. This is going from -1, +1, -1, +1. Those are the individual terms. So the series diverges because the limit does not exist. Here's another example. They want you to find the nth partial sum is given by this, and they want you to find the sum of the sequence. Well, if I look at the limit of the nth partial sums, it is 1/4. So the series converges to the partial sum of 1/4. Next, we have monotonic. Monotonic means it's either completely increasing or always decreasing. So looking at the derivative, we get the derivative is 2. The derivative is positive, so therefore the sequence is always increasing. It is not enough to say, oh, A2 is bigger than A3, and A3 is bigger than A2. You have to show it in general. So either in terms of the AN, which we could also do, so I could say AN plus 1 was equal to 1 plus 2n plus 1. And then AN, of course, would be equal to 1 plus 2n. And we can show that AN plus 1 is greater than AN just by substituting and seeing that it works for all n. Because here I'd have 1 plus 2n plus 2, and that is always greater than 1 plus 2n. In fact, it's exactly 2 greater. So we know that it is always increasing for every n. Okay, the next one is not something that you will have to do ever, but it just kind of explains what's going on. So here I found the nth partial sums, and all I did was multiply that by 2. So that's my first term, my second term, my third term, and I multiplied them all by 2, so 1/4. times 2, 1/8 times 2. If I add those together, actually subtract them, I'm sorry, you can see I get minus SN, and negative 1/2 is the only thing that doesn't cancel, because 1/4 minus 1/4, 1/8 minus 1/8. So we can see that our partial sum is 1/2. Later on, we go ahead and talk about this being geometric. And then a sum of a geometric looks like A over 1 minus R. So you can see we get the same exact answer once we get to geometric.